Okay, volumes by revolution. So we just ended the last test doing area under a curve, an area between two curves. That was all working with 2 dimensions. Okay, this stuff is now going to be 3-dimensional. So instead of doing area, we're going to be doing volume. So I want you to take a look at, this is called disks. We're going to find volume by adding up a bunch of disks. Well, what in the world does that mean? If you look at this graph, you can see just part of the line y equals 3x right here. Okay, now I could have asked you to find the area under that curve, and you could have done that with, geometric area formulas, because that would be a triangle, or you could have done that with calculus, right? From 0 to 1, it looks like what they have drawn. Okay, well, how are we going to change this now? How is this going to be different? Well, in order to create a 3rd dimension, or a 3-dimensional object, we're going to take that line, and like here you can see they have rotated it around the x-axis, and it's created a cone, right? Okay, so we are going to find the volume of that cone. And to do that, instead of with area, we add up a bunch of different rectangles, an infinite number of rectangles. Well, instead of adding up an infinite number of rectangles, we are going to instead add up, and you can kind of see this yellow piece, an infinite number of disks that would be, so they'd all have a different radius, but there'd be an infinite number of disks in there that we are going to add up. I have this graphic down here, so you can kind of, again, a lot of us are visual learners, so I have this YouTube video, that's what this link is. This link is this, so you don't need to go to that YouTube video. Okay, this shows again what it would look like to, that is showing rotating y equals the square root of x around the x-axis, and instead of a cone, it would be more like a cup, and there is right there, there's 1 disk. Well, we're going to add up an infinite number of those disks. Okay, so actually at this point, I want you to go watch this. I want you to pause my video, because this is exactly what I would do in class. This is exactly how I teach this when I'm with you. I stop class and we actually watch the Khan Academy video on it. Sal Khan does a great job of drawing these and showing you what they look like. So you don't have to try to write this down. This link is copied under the notes for this section. So go back to Power School Learning, go watch this video, and then come back. Okay. I want to generalize this. I know you just saw Sal Khan kind of go through this, but the big idea is that you're adding up these infinitely thin disks. Okay, now I'm going to have to show some sort of width, but we've got these disks, which is a cylinder, by the way. This is just a cylinder. Okay, normally I am better at drawing these, but it is hard with on my screen. Okay, so the width of these disks or cylinders, these are just cylinders, is dx. Okay, and then the height, okay, which is actually the radius, okay, the radius of that disk, going back to this image, the radius is just the function. Okay, how far am I from the center of this cone to the outside? That would be 3 times x, wherever x is. So in every problem, that is just going to be r equals f of x. Okay, well, again, we're calling them disks, and every textbook calls these disks, but this is really just the volume of a cylinder. And the volume of a cylinder is the area of the base, which is a circle, so pi r squared, times the height. Okay, so it's the same thing. Volume of this cylinder, this is a formula you use in geometry, is the area of the base, pi r squared, because the base is a circle, pi r squared times the height. Okay, well, to clean this up and make it applicable to what we're doing, it is pi times r becomes f of x squared. And then the height, well, the height is actually, since the cylinder is kind of laying on its side, the height of the cylinder is the dx. And that's part of what makes this so hard, is the fact that, you know, you did in geometry, you were looking at cylinders always like this. Okay, so the area of the base, pi r squared, and then, you know, this is your height right here. Well, this is turned on its side right here, okay? But they are the same pieces. So what we're going to do is we are going to add up all of these different cylinders. If we add up the infinite number of cylinders between A and B, we would have the volume of this geometric object. Okay, so we're going to use volume is going to be the integral from A to B. They'll have to specify. And then pi times f of x squared. Dx. Okay, and actually you can always move that pi outside because that is just a constant. Okay, so let's actually try this. This is what a problem would look like. Okay, they're going to give us how we should be bounding the area. Let's see, so 2 over x. If x is 2, y is 1. So I know this is a rational function. So it looks something like this. Okay, also going to be bound by y equals 0. So the x-axis, x equals 1. X equals 1 and x equals 6. Okay, and then we are going to rotate this around the x-axis. Oh, and I should have bound also, okay, so this is, and this. So the area we are rotating, this is the bounded area that we are rotating, and we are going to rotate that around the x-axis. Okay, so ultimately, what is this going to look like? I don't know how, kind of like a trumpet or a noodle, something like this is what it's going to end up looking like after you rotate it around. So, and then we're going to have all these different, we're going to have these infinite number of disks in here that we're adding up. Okay, so I'm going to go ahead and move that pi out front, and then we are adding up the volume of all of the disks from 1 to 6. Okay, so then our formula for volume is pi r squared times h. Well, I've got my pi right here. R squared is the function, so that's 2 over x squared. Pi r squared, and then times the height. Well, the height of each of these disks is dx. Okay, so this piece here, and then skip, this piece and this piece are the volume. And then the fact that I have the integral, that means I'm adding up an infinite number of volumes of disks. Okay, so that's it. And then this is where I'm allowing you, go ahead, plug this into your calculator. You should get 10.47. So it's going to be the same process every time. It's just going to be that the bounded area changes. Okay, however, I'm going to change things up a little bit. It's not always going to be a disk. What if the area isn't like this one? You see how the area here is snug up against the x-axis? Well, if it's snug against the x-axis, it's going to create a disk, right? However, if the area we're rotating, like this one here now, is not snug up against the x-axis, as in it's between two curves, you're not going to get a disc shape. It's not going to be like a bunch of quarters, like a roll of quarters. Instead, it's going to be like a bunch of washers. If you know what a washer is, a metal washer, not like a washing machine, but a metal washer, or a donut, you know, it's something hollow, right? Okay, so if you rotate this one around the x-axis, it's going to be like hollow on the inside, like a bowl. Okay, so this image, this graphic, sorry, shoot, it shows there's the disk that we just did, okay, because that one is snug against the x-axis, so it's going to create the disks that I mentioned. Might have to fast forward here. But disks, that's not even, maybe, huh. Okay, sorry. I do want you to, again, I want you to pause this and I want you to go watch the Khan Academy video and then come back. Okay, so the general idea with washers, well, the thing about a washer, I mean, it's still somewhat like a cylinder, but if you think about like in geometry, your teacher would often say, okay, can you find the area of that circle? Find the area of this circle here. Well, what you would do is you would take the area of the big circle, the whole thing, and subtract from it the area of the small circle, right? And that would leave you with the donut shape. Okay, well, the area of the big circle, for example, is going to be pi times the big radius, r sub b squared. And then the area of the small circle is going to be pi times r, and I'm going to do sub small squared. Okay, so in general, it's pi times the big radius squared minus the small radius squared. Okay, so how are we going to use this idea in an integral? Well, it's going to be very similar. It's similar to a cylinder. It's just a hollow cylinder, a hollow disk. Okay, well, so I'm going to go ahead and put that pi out in front. And we're going to go from some a to b value still. But we've got pi, and then instead of r squared, we have to deal with this right here. We have to deal with getting that donut shape. Okay, so it's going to be pi times whatever the top function is, I'm going to call it f of x, and above it I'll put, that's the top function. Okay, so back to the image here. The top function, I mean, this is just like what we've been doing. That's the top function, and then the curve is the bottom function. So top function squared minus, we'll call the bottom function g of x. And that's the bottom function. And then dx. Okay, so that's the general idea. Let's try this. Okay, so I've got the line y equals 2x. So slope of 2. And then x squared, so you can see where they intersect. It's just this little sliver right here. Okay, so when I rotate that around, if I were to take that and rotate it around the x-axis, it's going to create, like, on the outside it's going to be flat, but then on the inside where you could like put stuff, water, you could, like a cup, like a bowl, you could put stuff in it. Now it's going to be pointed, so it's not like if I were to turn this on its side that it would sit up, okay, because maybe it's more like a top. So rotating that around. Okay, so the volume would be, I'm going to move that pi outside, and then the x values we're going from are 0 to that point of intersection, which is 4. Oh, sorry, the y value is 4. The x value is 0 or 2, 0 to 2. Okay, those are the x values that the area covers. Okay, and so then pi, and then instead of r squared, it's a little more complicated. It's r squared minus r squared. So the top function is 2x, so 2x squared minus, this is interesting, x squared squared, and then dx. Make sure you put parentheses around this when you plug this into your calculator. I'll let you do that. Go ahead, pause, do that. You should get 13.4. Okay, so for your homework, there is a worksheet posted on PowerSchool Learning that you need to spend some time today practicing. Please email me if you have questions.